Welcome to the session. In this lecture, we'll see the different applications of op-amp. We'll start with non-inverting. In last lecture, we discussed about inverting amplifier. So in the case of non-inverting amplifier, if I'm considering open loop gain as infinity, I can get the expression of closed loop gain V0 by Vin as 1 plus Rf by Ri. But here we'll see the effect of finite open loop gain by considering that the open loop gain of op-amp is not infinity, the A value is finite. So to get the new expression for closed loop gain, so V0 by Vin in this case is nothing but your AF. So to get the new expression, first what I can do here is now this is at V1, Vin and this is at V1. Why these two are different potential is because I am considering op-amp is having a finite open loop gain. So this is at some potential V1 and this is at Vn. Now the difference in the potential multiplied by open loop gain is the output voltage. So Vin minus V1 into A is nothing but V0. So in that using that, if I write, I'll get the equation for V1 as Vin minus V0 by A. So after doing that, what I can do is I can write a KCL here. The current flowing through Ri is Ia and this is If. And if we equate these two, those two currents, and by substituting the value of V1 there, I'll get the expression for V0 by V and the new expression, that is this value. If you compare with the ideal value, when the value of A equal to infinity, this term becomes 0, this will be 0. So the expression is 1 plus Rf by Ra. So with finite open loop gain, the closed loop gain modifies as this one. Right. In the inverting amplifier, we have seen the input impedance of inverting amplifier. The input impedance is nothing but the resistance connected to the input. Now here, the input impedance is, can you comment the input impedance here? If you look at the circuit, the current flowing here is nothing but 0, right? Since the current flowing is 0, input impedance is input voltage in input current. Since the current is 0, input impedance is infinity for a non-inverting amplifier. And one very common application of non-inverting is by connecting a feedback just by shorting output to input. So this we used to call it as voltage follower, and the feedback what I applied here is a unity gain feedback. There is no, the feedback is simple, the output and one input is shorted together. Now in this case, Vout will be equal to Vin only when your gain is, open loop gain is infinity. If your open loop gain is infinity, the open loop gain is infinity, A is equal to infinity, this potential will be same as this potential by virtual ground. That will be same as, so V0 will be same as Vn. So this is true when op-amp is having an open loop gain infinity. Now with the finite A value, and the A value is finite, you can write an equation Vin minus V0, that is the difference between the potential, difference between the input potential multiplied by A is nothing but V0. So that is Vin into A, we can write in this fashion, and finally you will get V0 by Vn as A by 1 plus A. So ideally, this will become infinity only, this will become 1. V0 will be equal to Vn only when A is equal to infinity. Other case, there will be an error always, that error is 1 by 1 plus A. Right. Yeah. That is a voltage follower. Similarly, we can see some other configurations. One is trans resistance amplifier. When I say trans resistance amplifier, input quantity is current and output is voltage. So in the circuit, you can write output as, the current is flowing in this fashion. So V0 is nothing but minus In into R0, or V0 by In, that is the trans resistance, that is equal to minus R0. So in this circuit, gain is nothing but, instead of gain we used to call it as the trans resistance, because output quantity is a voltage and input is current. Similarly, trans conductance amplifier. So trans resistance we obtained by slightly modifying the inverting configuration, and trans conductance will obtain by slightly modifying the non-inverting configuration. So you can just look at the circuit and we can say output voltage V0 is nothing but 1 plus R dash by R dash into the potential here VA, as same as a non-inverting, right, non-inverting amplifier configuration. Now how to get VA? You can write the expression at VA here. So I can write VA in terms of Vin or IL or whatever we want, we can write that. Right, so the expression will be 1 plus R dash by R. That is 2 times VA. Ideally, it is 2 times VA if you use the same resistor value. So the transconductance is nothing but 2 in that case. Yeah, it is the just output is 2 times VA. So by choosing the different ratio, we can get different values over there. Now the next one is a difference amplifier, which is a very important configuration using op amps. Difference amplifier, or it's a differential amplifier. The basic idea is output will be nothing. It will be the amplified version of the difference input V2 minus V1. So Vout will be V2 minus V1 multiplied by the gain of the circuit. So here in this circuit we'll try to find the differential gain of the circuit, common mode gain of the circuit, and differential input resistance. These three parameters, we'll see how we can obtain these three parameters for a difference amplifier. So here there are two inputs V1 and V2. Since there are two inputs applied to the circuit, what you can do is you can consider one at a time, and you can find the effect of that input at the output, and finally you can combine both things. That is nothing but apply superposition theorem. So to find the gain, you can apply superposition theorem. So first we'll find the output due to the input V1. So what I'll do, I'll short V2. That is what I have done here. V2 is shorted to ground. Now this is as same as so when these two, this is shorted to ground, R3 and R4 there are two resistors which are connected in parallel, right? And as there is no current flow there, the potential is nothing but 0. So the circuit resembles as an inverting amplifier. So I can write Vout1, that is output due to input V1, as minus R2 by R1 into V1. Similarly, you can do the other way. To find the output due to V2, that is Vout2, you can short V1 to ground, and when I do that, the circuit looks like a non-inverting amplifier, and the gain is Vout2 is 1 plus R2 by R1 into the potential at this point. That point is V2 dash. Now how to get V2 dash in terms of V2? V2 dash is nothing but V2 into R4 by R3 plus R4. So by including that, I can write Vout2 as 1 plus R2 by R1 into R4 by R4 plus R3 into V2, or slightly by modifying, I can write this as R2 by R1. If I can take common, it is R1 by R2 plus 1 into this R4 I have taken to the denominator, so 1 plus R3 by R4. Now one condition I am applying here, R1 by R2, this ratio is same as R3 by R4. Under that case, I can write Vout2 as R2 by R1 into V2, because R1 by R2 is same as R3 by R4, so I can cancel these two. It is same as R2 by R1 into V2. So the final output, I can combine the outputs of due to V1 and V2, and if I combine, I'll get the expression like this, or if I take common R2 by R1, it is V2 minus V1. So V2 minus V1 is the differential input VID. So I obtain differential gain here as AD, which is Vout by VID as R2 by R1. Right, or if I choose R2 by R1 as 1, output is nothing but the difference of the two inputs. The circuit will act as a difference amplifier. If you want some gain, you can choose R2 by R1 value accordingly. So this is differential gain of the circuit. Now if you want to find the common mode gain of the circuit, what you can do is you can short the two inputs together, and you can apply a common signal VICM. Now if I apply VICM here, the potential at this point and this point will be same by virtual ground property, and the potential there will be VICM into R4 by R3 plus R4. The same potential will be at this point also. Now the current I1 here is the voltage at this point, VICM minus VICM into, so output voltage for the circuit is voltage from this point to ground, that is voltage across R2, and voltage across R2 plus voltage from this point to ground. So the voltage at this node is VICM into R4 by R4 plus R3 plus drop across R2 will give you output voltage. The output voltage, since the current is flowing in this direction, output voltage is minus I2 R2 plus this node voltage, and I2 is same as I1, both currents are same, and that current is equal to VICM minus VICM into R4 by R3 plus R4. By this node voltage is VICM and this is, we already have written, so that difference by R1 will give you I1. So you can substitute the same current I1 as I2 here and will obtain output voltage expression as this one final. So this is nothing but your common mode gain. So you obtain common mode gain here, differential gain on the top, and we know that common mode gain should be ideally 0, and that is possible when your R1 by R2 is same as R3 by R4, the same assumption what I have taken for the differential gain. In that case your common mode gain will be equal to 0. And now for the same circuit, if I want to find differential input resistance, I'll be connecting a source here to find differential input resistance from this point. By connecting a source, the current IID is flowing here. By considering a virtual short here, the same current will be flowing across this loop. And if I write a loop equation, VID minus IID into R3 minus IID into R1 is equal to 0, which gives your VID by IID, which is the differential input resistance as R1 plus R3. If both are same, I can write the differential input resistance as 2R1 or 2R3. So this is a question which is asked in semester end exam, last fast track exam. You can look at the question. Obtain the expressions for the differential and common mode gain of the difference amplifier shown in figure 8a. So you can get the same expressions, you can derive the same expressions as above and determine these gains for, so after getting the expressions, you can substitute the values for R1, R2, R3 and R4, and you can get the values of the gains and also determine the differential input impedance. It is for 8 marks. So you can try this question. It's all about difference amplifier, and in next lecture we'll see few more applications of op-amp. Thank you.